So we start with video lecture 11, and most of it is there in the first two PDFs that I sent you, PDF 1 and PDF 2. But I will, for this lectures, for the next two lectures, I will try to bring in a little more logic and why it is done and why it's not done, and what is there are more angles to those equations which are not there in the PDF, and I will highlight that to you. Now the first thing is, we were so long, for quite some time, talking about reactions. We need reactions, independent reactions, number of phase components minus system components, and we said these are, and there are variables. So obviously the reaction translates into some sort of a equation, a mathematical equation, from where the variables are. But till now we don't have it. So now we try to bring in these reactions, equations from the reactions. Now, as in thermodynamics, we are talking of equilibrium thermodynamics. We are not talking of unstable equilibrium, we are talking about stable equilibrium. Now, what is the difference? Just to illustrate the point, say for example, you have a ball, you have two balls like this, and they are falling under gravity, and this is, when they reach here, that's stable equilibrium. Stable equilibrium. If we draw it the other way around, so you have a ball, and it can have a free fall this side, and you can have a free fall here. This is a situation, what is called unstable equilibrium. But what we are studying now is essentially this type of a situation where it's stable reactions. Equilibrium, stable equilibrium. In other words, if you have reaction rates, there's another way to look at it. Say for example, this is time and this is reaction rates. So what happens with reaction? The products decrease, and so the reaction rate normally has a slope like this for the product, for the reactants. The number of reactants decrease, and the back reaction, for example, and the products increase. So this is a situation where we have a stable equilibrium, which means to say that the number of products, number of reactants, they react to produce a product, and the product also produces the reactant. So it's sort of a stalemate over which we see the situation. This is clearly not the case. Why? Because say for example, I drew a reaction of a corona texture. Say you have a mineral and there is a corona growing in this, and a part of the mineral of course is consumed and a new mineral forms. So if this is B, this is C, this is A, and this is C, then we write a reaction A plus B is equal to C. But here what we see is C has grown at the interface between A and B. So essentially the reaction should be A plus B equal to C. This is how it should be. A plus B reacts to produce C. A plus B is equal to C is then the amount of A plus B that has reacted and produced C, the same amount of C goes back into it. It doesn't really hold in geologic systems. So either you have a forward or a backward reaction that works. But what we can imagine here is that although this is the actual situation, but we can approximate the situation here by taking this type of a reaction, A plus B is equal to C, meaning that A plus B that is produced to produce C, C reacts to produce 1, so it's sort of a stalemate, where both the reactant and the products are in an equilibrium, in a stable equilibrium. We assume stable equilibrium, but this is not stable equilibrium. This is unstable equilibrium because the actual reaction is A plus B produces C. But chemical thermodynamics deals with stable equilibrium. Now, what we are trying to do here is, so we will be dealing with this sign, equal to sign, and not the arrow sign. But like fractional crystallization, for example, you have studied, I hope, in Indian petrology. So a fractional crystallization is like a behavior equilibrium crystallization. So this actual reaction can be imagined as different stages of a reaction. We won't go into that in PTT parts, etc. Those are a little more advanced in the way that we take it. But we try and understand first basic stable equilibrium involving reactants and products. And in thermodynamics, it's always the products minus the reactants. That's how it always goes. A plus B, products minus the reactants. Any thermodynamic parameters is product minus the reactant. Now, when such a situation arises, it becomes important for us to understand how these reactions look like from a sense of thermodynamics. Now, say for example, if we have a reaction A plus B is equal to, say, C, then we must understand if G, for each of, these are not written, say for example, I will give you an example, that's the best. So, say MgFe2Si2O6 is produced through a reaction Mg, Fe whole twice SiO4 plus SiO2 is equal to Mg2Fe2Si2O6. Right? So this is the actual reaction, or olivine plus quartz is equal to orthopyroxene. But from a thermodynamic viewpoint, we always write reactions in terms of phase components. Phase components. So this type of a reaction is just a model reaction. It is not an actual reaction, although in actuality it works like that. But a model, but this is not how things are written. Reactions are written in terms of phase components, not phases. So say for example, this reaction can be written as Mg2SiO4 plus SiO2 is equal to Mg2Si2O6. So this is MgOSiO2 end member, or you could write this reaction as Mg2SiO4 plus SiO2, and this is Fe2Si2O6, and this is FeO-SiO2 system. Although the total system, this system, is MgO-FeO-SiO2 system. The total system here is MgO-FeO-SiO2, but when we have to write it in terms of end members, then you have, this is an MgO-SiO2 system, end member reaction. This is an end member FeO-SiO2 end member reaction. And if you algebraically add these two to eliminate SiO2, you will get a reaction Mg2SiO4 plus Fe2Si2O6 is equal to Fe2SiO4 plus Mg2Si2O6. Now this reaction is in the NGO, FeO, SiO2 system. But this is an reaction that involves exchange of magnesium and iron between olivine. Here you can see Mg2SiO4, Fe2SiO4, and here you have Mg2Si2O6, Fe2SiO6. The important point here is, in these reactions, the product is different from the reactant. Here you have orthoperoxine, quartz, olivine. Orthoperoxine, olivine, quartz, orthoperoxine. So here the product and the reactant do not have the same phase. But if you see in this, you see you have olivine here, you have orthoperoxine here, you have olivine component again, and you have orthoperoxine component again. So this is a particular type of reaction. It's of great importance, but this is a particular type of reaction in which the phases occur on both sides. It's the same phase essentially. Only thing, the components are different, as you can see. Mg2Si2O6, Fe2Si2O6, the components are different, but the phase is the same. So it's a magnesium-iron exchange between olivine and orthoperoxine. These two are related to this. So any two of these three reactions are independent reactions. Right? So now we try to get into a little more of chemical thermodynamics. Now, for any reaction, I will write this as an example. Say Mg2SiO4 plus SiO2 is equal to Mg2Si2O6. For Mg2SiO4, I told you it is like this. The subscript is phosphorite, superscript is olivine. Phase component here with a lowercase and phase here starting with an uppercase. So here also G, Si, you can write here instead of, you can also write G, SiO2 quartz. And you have G, enstatite, orthoperoxine. So Mg2SiO4 has a free energy term, SiO2 has a free energy term, and G has a free energy term. These are the three free energy terms. And what is the delta G of the reaction? It's the product minus the reactant. So it is G enstatite opiates minus G forsterite olivine plus G quartz in quartz. Product minus the reactant. Have you understood? So this is the total free energy of the reaction is del Gr is equal to 0, G enstatite, G forsterite, and G quartz. Now at equilibrium, delta Gr, this delta Gr, free energy of the equation is equal to 0. Why? I will give you an example. Say for example, here I am taking a reaction L2SiO5 sillimanite is equal to L2SiO5 in kyanite. So the phases of equilibrium are the phase component L2SiO5 sillimanite, L2SiO5 kyanite. So for this you have G L2SiO5 in sillimanite and Gl2SiO5 in kyanite. Not is equal to is this. So kyanite has a free energy and sillimanite has a different free energy. Now since if we take only this as Al2SiO5 system, pure system, then G, as I told you, is a function of temperature. G is a function of temperature. So what happens at temperature? G is a function of temperature and pressure, but not composition, because these are all pure phases. So there is no composition term involved. So it's a function only of pressure and temperature. Now if you take an isobaric system, let's say we take an isobaric system. Now isobaric system means P is equal to constant. That would mean dP, the derivative of it, is equal to 0. For a constant, the derivative is equal to 0. Now you see, this equation, if this is G, temperature, and this is pressure, we know that sillimanite is the high temperature form, kyanite is the low temperature form. So I draw two reactions like this and like this. I draw two reactions like this. Now you see, and at this point. Now you see here, at which is the stable polymorph? The one which has lower free energy. So this one will be the free energy for sillimanite, because we know that sillimanite is stable at high temperature, and this is for kyanite. Right? Now at this, on this side of the temperature axis, G is like this. Now you can ask me, why did you draw negative slopes? Please hold it. I will let you know in one or two classes. I will let you know. So why is there a negative sign? Just quickly, G is equal to H minus Ts plus PV. Right? Since we have taken P is equal to constant, this is no more a variable. So G is equal to H minus Ts. So you see, if you increase temperature, this negative term becomes larger. So a larger negative term is subtracted from the H term. So what happens? All the slopes of the reaction have a negative slope. Less, more, it's unimportant, because if S is constant, if you increase, then you have a larger term, progressively larger term at higher temperature being subtracted from this. This is called G, to decrease with temperature. So this is sillimanite and this is kyanite. Here, G sillimanite is less than G kyanite. But if you are here, then G sillimanite is greater than G kyanite. So here, kyanite is stable, and here, sillimanite is stable. But at this point where the two curves intersect, G sillimanite, at this point, G sillimanite is equal to G kyanite. And if it is like this, then the delta GR of the reaction is equal to 0. Right? So for all expressions at equilibrium, the free energy change of the reaction at any pressure temperature condition is equal to 0. If you start with the reaction with an equal to sign, as I have shown here. So at delta GR is equal to G instantide orthoperoxide minus G phosphoride, G olivine, etc. is equal to 0. So the change in free energy, product minus reactant at equilibrium pressure temperature condition is always 0. So we have this expression. But we also know G is equal to G0 plus RT ln activity. We also know this. We also know this G is equal to G0 plus RT ln A. Once again repeating, if it's a pure phase, then activity is equal to 1 and RT ln A is equal to 0. So it is G is equal to G0. And what is G0? G0 is the energy of the phase component if it's pure at a particular pressure temperature condition. At any pressure temperature condition or at a particular pressure temperature condition, G0 is the free energy contribution of the pure phase component. Pure phase component. Okay? It's also important, and this will come back here, G minus G0 is equal to RT ln activity. This is very interesting. G minus G0 is equal to RT ln A. So the difference between this G, what is this G? Is the total free energy of the phase component. What is G0? Is the free energy contribution of the pure phase component. And therefore this is the contribution of impurity in the phase component. And typically, since in an impure phase activity is less than 1, this whole term is always negative. This whole term is always negative. So you remember this, that's RT ln A activity is equal to G minus G0, where G0 is the free energy at equilibrium Pt of the pure phase component and G is the free energy of the phase component. Whether it is pure, whether it's impure, it's unimportant. G is the free energy at equilibrium pressure temperature condition of a phase component. And G0 is the free energy of the phase component if it were pure at that pressure temperature condition. Please remember, this is very important. If I write it exclusively, it should be GPT minus G0 PT is equal to RT ln activity PT. That's how it should look like, if I have written it correctly. What is G0? It's a free energy term. So RT ln A is also a free energy term. Totally is free energy term. Either in calories it's given or in joules. This I said before. Now what is G0? G0 is, this is from part 1 of the thermodynamics of pure phases. G0 is equal to, G0 PT is equal to H01298 or yes plus integrate, I'm giving an arrow, Cp into dt 298 to T minus T 298 to T of Cp by T dt plus volume as a function of pressure dP from 1 to P. This is what is written, derived in the first diagram. So what is it? Oh, I forgot to, sorry. This is how it is. G is equal to H0 PT minus TS0 PT plus integration of Cp dt minus T Cp by T dt and integration of 1 to P Vp dp. Now what is this 1 and what is this 298? 1 is 1 bar, which is the surface temperature. It's also equal to 10 to the power of 5 pascals. And 298 is nothing but 25 degrees centigrade, 25 degrees centigrade plus 273, so that is equal to 298 kelvins. All thermodynamic parameters, their effect from 25 degrees centigrade and 1 bar or 1 atmospheres is 10 to the power 5 pascals. So this is the integration that gives you from the standard state to the required pressure temperature condition. If you have to do this, then your G0 PT is equal to this. This is your G0 PT. This term here, G0, this term here, expression is G0 PT. This I have written obviously for a pure phase. If it's an impure phase, this RTLNA should go here and add up here as plus RTLNA if it's not a pure phase. Now what happens for us is, this equation is fairly complicated, as you can see, because the derivations, integrations, etc., it makes it very cumbersome to look at, although that's true. Whatever I've derived is absolutely perfect. But the important thing is, when you have so big equations, you know from your chapter 1 of that derivation of the pure phases, when your equation becomes so big, then it's sometimes very difficult to find out what's really happening. What's really happening? That becomes a little bit of a problem. Our outlook would be that, okay, we remove the complications and see the simplified picture, so we try and understand the logic of it. Our point is, we want to understand the science of our thoughts. All complications, etc., can be added. That's not the issue. Once you know the basic theory, then you know how you can develop on it. But we should first try to get is the basic theory. For that, I will make a few assumptions. And those assumptions actually, they are not very valid. If I use it, they are going to throw my paper into the next waste paper basket. They will not. They will not accept it. But for our teaching, for you to understand, we can do some simplifications. I will tell those. You know, when you were in class 6, 7 and 8, you were dealing with problems on triangles, etc. You know, it's called Euclidean geometry, where you had a paper and you could draw your triangles, etc., etc. So the surface was all considered as flat. But when you went to class 10 or class 11, I don't know when it's taught, then you went into something called solid geometry, where the surface is now curved. Have you understood? But first they never told you that the surface was curved. Or even if they told you, they say it's a huge curve, so if I take a small segment, that part is flat. Either of the two logic. Either they said it's completely flat, or they said that we took a very big curvature, out of that we took a very small piece, so on that small piece everything is flat. So something like Euclidean geometry. You learn to understand the basic idea of geometry. When it came to solid geometry, the theta angles, then of course it becomes a little more complex. Similarly for us, we do it the Euclidean way. We forget the frills, the fuss. We try to make things simple so that we understand the science of it. So, in order to do that, the first thing that I will do is, if you look at your part 1 paper, this H0PT comes from a term, actually, yeah, you can see it, otherwise again I have to derive it. So, what we consider here is, we consider that the effect of this is equal to 0. That means, we are ignoring the heat capacity terms, which would have affected your enthalpy, pressure, temperature conditions, and entropy. We assume, we neglect it. Have you understood? We neglect it. And another thing here volume is taken as a function of pressure, but we assume that the volume is independent of temperature and pressure. The volume is independent of temperature and pressure. So this term boils down to integration of 1 by P into VdP. That means equal to V into P minus 1. Have you understood? So we do two approximations to this. One is, it's very important that you realize the right equation is the one that I give in the black. But we ignore that for the moment. And we say, okay, let's ignore the heat capacity term. These are very complex terms, but they are needed. They are truly needed. So you ignore the heat capacity terms. And V, volume of a phase, obviously if it's not incompressible, if it is compressible, then it is a function of pressure and temperature. We assume that our solid is incompressible. That means volume is not a function of pressure and temperature. It's a constant. So if we do that, then V comes out and you have P minus 1. So if we do that now, the equation becomes a little simpler. This expression now becomes a little simpler. How simpler? It reads now G0 PT is equal to H0 I'm sorry here, I made a mistake. Sorry, please make the correction. This is how it is written. So what we write here is H01 to 98 minus TS01 to 98 plus V into P minus 1. Now normally pressures are quite high, 6,000, 7,000, 8,000 kilobars, and so we can approximate this as not P minus 1. We can ignore this and write P into V. So we drop down the equation to a much simpler form by, sorry, I made the mistake, you should make the correction, you should also check part 1. That CP, we have ignored the heat capacity term and we have considered that the volume of the phase component does not change. That means it's an incompressible solid. So it's not a function of pressure and temperature, and this is V into P minus 1. And since P values are much, much bigger than 1, we ignore the minus 1 term and write V is equal to P. So this makes the equation much, much simpler to look at. It's easier to do it. But this equation is a highly simplified equation that in the modern day you can't use it. But it really helps you in trying to understand the expression. It tries to understand the expression, and that is what we are aiming at. So now if I do this, then I erase this. And I write this one, G0, Gn static. How will I write this? You know, for every phase component, GPT is equal to H01 to 98 minus TS01 0, 1, 298 plus V0, 1, 298 into P. That's our expression. If it's a pure phase. If it's an impure phase, you have plus RT ln activity. This is your term. Right? Now, several important things. This part of it is essentially G0 PT. This term is G0 PT. And this is RTLN. So you have GPT is equal to G0 PT plus RTLN activity. If it's a pure phase, as we said before, G0 PT is equal to GPT. Now, if you know the pressure temperature condition, then this term is known. Why? Because to know this, you should know the thermodynamic parameter enthalpy, entropy, and volume. The rest is, it's a function. So the equation is essentially a function of two variables, pressure and temperature. These are the two variables in the expression. Whereas these thermodynamic parameters, H, S, and V, are known almost for all phases, either from theory or from experiments or by retrieval calculations. We will do one or two retrieval calculations. These are all well known. Right? So now we can write here now for this expression. So this expression we can break up and we can write G0 PT OPX. This we can write, not G0. Okay. This one we can write, so G Einstein OPX will be equal to H Einstein 0, 1, 298 OPX minus TS Einstein 0, 1, 298 Einstein or OPX plus P into V Einstein 0, 1, 298 OPX. So we can write, similarly, we can write for G Einstein, then we can write for G Fosterite in olivine, and we can write H Fosterite 0, 1, 298 olivine minus TS Fosterite 0, 1, 298 olivine plus P into volume Fosterite 0, 1, 298 olivine. And similarly, you will have G quartz in quartz is equal to H quartz in 0, 1, 298 quartz minus TS quartz 0, 1, 298 quartz plus P into V quartz 0, 1, 298 quartz. So we have three equations of state 1, 2, and 3. We have three equations of state. Have you understood? So essentially, in all this, the variables are temperature, pressure, temperature, pressure, temperature, and pressure. This is how it goes. And by algebraic summation, what we can write, delta H instantite 0, 1, 298 OPX minus T into delta S forsterite 0, 1, 298 olivine plus P into delta V quartz in 0, 1, 298 quartz. And this is equal to 0 because del GR is equal to 0. And this we have replaced by this. So what is our delta H instantite? Delta H instantite, sorry. I'm a little sleepy today, it looks like. This is what will happen. Del HR minus T del SR plus P delta VR. You see, these are important. Delta, delta, delta. So what is delta HR? Delta HR is equal to H01 298 instantite minus H forsterite 01 298 plus H quartz 01 298. That's it. So you have delta HR, which is this term. Delta HR is equal to H instantite minus H forsterite plus H quartz within the third bracket. So this is how it will go. Similarly for delta SR and similarly for delta VR. I will write for delta VR is equal to volume instantite 01 298 minus volume forsterite 01 298 plus volume quartz 01 298. Similarly for entropy. So this is the basic equation. And once again, all these parameters are known. The only parameters that you don't know is temperature and pressure, and is equal to 0 for pure phase. It's pure phase. This is pressure and temperature are the unknowns. All other parameters, thermodynamic parameters, are known either experimentally or from phase equilibrium studies or retrieval calculations, different ways, but all are known. Right? So that is the type of expression, equations of state that you get. So for this reaction, this is the equation of state. It does not matter if you have reversed the reaction. For them, say for example, you could have, since it's equal to, you can reverse the reaction. In which case, your delta HR will become negative, delta SR will become negative, delta VR will become negative, but all negative, and it becomes the same expression. Only thing, you have to be careful, you have to write the equation first. It stands to reason, therefore, that if pressure and temperature is known, then the whole expression becomes equal to 0. Whole pressure temperature is known, the whole equation breaks up into 2. Your only variables in this are pressure and temperature. Now, I will introduce you a little bit. So this is about pure phases. Now we'll go a little bit into solid solution phases. a little bit into solid solution phases. Now, again starting with G is equal to G0 plus RT ln activity. Now, this activity term is a complex term. It can be written as G is equal to G0 plus RT ln x into gamma, where x is the mole fraction which we were talking so long, and gamma is called the activity coefficient. Activity coefficient. This is the expression, and this is where the phase component is impure. The phase is impure. Otherwise, this term is not there. Only when you have a solid solution phase, activity comes in, and activity essentially is equal to x into gamma. Activity is equal to x. Now, if we plot if we plot a diagram where this is activity and this is mole fraction, and A is equal to x into gamma, or I am writing it, I will use it, that is why I am writing it, or gamma is equal to A by x. A by x. Now, several things can happen. Your activity composition variation could be like this along a 45-degree slope, which is where A is equal to x. A is equal to x. It's a 45-degree line, which means gamma is equal to 1. Such type of mixing is called ideal mixing. Ideal mixing means gamma activity coefficient is equal to 1, or activity is equal to mole fraction. Right? This is what is called an ideal solution. But AX relationship can become very complex. So say, for example, you could have a situation where it could be like this, or for example, it could be like this. What is here on this side? You see, for a particular value of x, A is larger. So here, this is called ideal solution. Here, A is greater than x. That means gamma is greater than 1. On this side of the diagram, A is greater than x. A is greater than x. That means gamma has to be greater than 1. And on this side, A is less than x, and therefore gamma is less than 1. Right? These are, it can become very complex, but these are two end-member things. One is called ideal solution, and the other, any other variation, is called a non-ideal solution. Non-ideal solution. That means gamma is not equal to 1, or A is not equal to x. Those are non-ideal solutions. This is called, where gamma is greater than 1, this is called positive deviation from ideality. Positive deviation from ideality. And this here is just the opposite. negative deviation from ideality, where gamma is equal to is less than 1. But both are non-ideal solution, as opposed to this equation where A is equal to X. Now, this part you note very carefully. I told you, as X tends to 0, activity gamma tends to 1. So, at very high dilution, that means X tends to 0, gamma tends to 1. That means most solutions, ideal or non-ideal solutions, they tend to become as an ideal solution. Ideal solution remains ideal solution, but non-ideal solutions also tend to behave as ideal solution in extreme cases. Right? Now there is something important, and this is here, for example. Now say, for example, I take a point here and draw a tangent. You take a point here and draw a tangent. I take a point here and draw a tangent. What is tangent here? You can see this. If this is the tangent, this axis is A and this axis is X. So when I draw a tangent, essentially it is A divided by X. That means this is gamma. Right? As this is gamma. Here you see what is happening. Gamma on this curve, gamma is nearly infinity. Here the gamma has a finite value, and here the gamma has a 0 value. But you see, this is the X value here, this is the X value here, and this is the X value here. So what has happened? What has happened? Along this graph, gamma is a function of X. Have you understood? Or A is equal to a function of X. A is obviously a function of X, because even in ideal solution, A is still a function of X. But here, for ideal solution, gamma is not a function of X, because gamma is equal to 1. For ideal solution, gamma is equal to 1. That means it's not a variable parameter. Irrespective of any X, it has the value 1. But for a non-ideal solution, the gamma becomes a function of composition. So, what happens? The activity, therefore, activity term is A is equal to X into gamma. If the gamma term is also a function of X, then it becomes a very complex function. The activity becomes a very complex function. Similarly here, you take a point and you draw a tangent, take a point, you draw a tangent, take a point and you draw a tangent. You see, the F value becomes a complex function of composition. So this is where I will stop today, saying that you have ideal solution where gamma is equal to 1, gamma is not a function of X. And non-ideal solution is where gamma is a function of X. That is the difference. And gamma is less than 1 here and is more than 1 on the other side of the A is equal to X diagram, which is a non-ideal solution. So you can imagine that if you have to deal with ideal solution, you're dealing with a simpler case. If you're dealing with a non-ideal solution, you're dealing with a much more complex equation, because you should know how gamma varies as a function of composition. But for ideal solution, gamma is not a function of composition. Have you understood? It's equal to 1. So again, as I have always maintained, that we take things simply. We don't make things complicated. So first, we will deal with ideal solutions. So first approximation that we did was we neglected the entropy term. Then what we did, we assumed the solids as incompressible. They are not a function of pressure and temperature. And the third assumption that I am taking here is that all solutions, just for our sake, all solutions are ideal solutions. We'll begin with that and go into non-ideal solutions. Have you understood? Right. I think I will stop here. I will have one more, at the end of it, I will have one more video lecture for this week. Right. Thank you.